Hello. Right, yes, using maths to bend the world to your will, aka a gentle, quick whistle-stop tour of the basics of control theory. Ooh. So, we can have some sort of physical process. We've just heard about physics. An engineer might call it a plant. But we're mathematicians, so maybe we'll just call it physics. And we can represent physics with some sort of function, with an input and an output. Here's an example of some physics. It's a mass spring damper system. We let it go, it wobbles about a bit and settles down. And we can use maths to describe this. We can have a transfer function, sort of the output of, divided by the input or something like that. The input, which I haven't drawn here, is we're applying a force to the system from externally. Right. So we take this physics, and let's say we want to change the way that it works. So we can maybe take an inverse function or something like that to undo it. But more generally, we've got the laws of physics, so we can have control laws as well. And in an ideal world, we might be able to invert the function and all the rest of it, but in reality, we're never going to get that accurate, and inverting functions is hard in general, so we'll have some feedback. So that allows us to take the input we want, compare it with the output, and get an error signal. So here's a tool that we can use. This is a frequency response of the piece of that mass spring damper system, and we see a nice little peak where it's in the magnitude, and then the phase has a nice sort of change from 0 to minus 180 degrees at that sort of resonance point, which corresponds to where it was wiggling up and down. And here's another tool we can use to look at it. This is called a pole zero plot. The details of what the axes are isn't too important, but we see these two x's, which is where this equation blows up to infinity. And the position of those is kind of important because it allows us to see some interesting things. A little bit more on that later. By far the most common technique that's used to control something, so the most common control law is called PID control, because we've got a proportional term, an integral term, and a derivative term, so fancy naming there. This is the only equation you're going to see as a function of time. Everything else in this talk is in the S domain, which if you were at my talk 3 years ago, you'll recognize as being the result of the Laplace transform. Trust me, it makes all of this about 1,000,000 times easier. So now we'll go through a little works example. We've got these various bits and pieces on the screen. We're going to look at a step response, so what happens when we change the input we want from 0 up to 1. So we've got, on the top left, we've got the target line where we want to be. And we'll start by just increasing the proportional term. We've got some wiggles, but we end up settling on a sort of equilibrium, about halfway between where we started and where we wanted to end up. So it's helping, but it's not all the way there yet. And to fix that, we need to use the integral term. Now that allows us to sort of reach an asymptotic sort of behavior, as we'll see here. And if you look at the poles in the bottom, oh look, it's gone bananas as they cross the axis. So we'll dial that back a little bit. So this is actually one important thing. It goes unstable when the poles go, and when the poles reach the axis. And that's one of the really important things we can look at for stability, and how far they are away from these poles, from this axis, allows us to see something about the robustness of the system, so how resistant it is to disturbances. Speaking of disturbances, we can try and get rid of some of those wiggles with the derivative term, which gives it, if you see on the frequency response, the right-hand side of that just came up a little bit, indicating that it's got a sort of high frequency response there. And we can get rid of all the rest of it by dialing back the proportional term, and look what happens. Oh, there's a couple of zeros have just appeared, which are nicely cancelling out the poles. And that is how we get a nicely controlled bit of physics doing what we want it to do, not what the physics wants it to do. So just to sum up, this only works when you've got a linear time invariant system, and it allows us to study the stability of a system and the robustness of it. But we can use it for a lot of nonlinear systems because we can linearize them. If you want to know more about that, because there's a lot more, come and ask me in the break. And that's been it. Thank you very much.